and welcome to this video on periodicity. This is for OCR A. My name is Chris Harris and I'm from AlleryTutors.com, and basically in this video we're going to do a quick overview for revision purposes of the topic of periodicity. Now these slides that I'm going to use, you can use them yourself. You can purchase them from the link in the description box. If you just click on that and you can use them there. Great for things like revision. You can use them in your phone, your tablet, print them out, do whatever you want with them really. But it's just a good supplement to all the other revision material that you've got, and then you can cycle through it and listen to this video at the same time. So there we go. Yeah, so this is dedicated specifically for OCR A, and you can see we've taken the specification points and put them on here, and this basically just shows that the PowerPoint matches the specification that's required. So if you do OCR A, you should be okay. Right, so we're going to start with the historical periodic table. Arguably, the periodic table is the most important bit of scientific development ever. I'm going to say that because I'm a chemist, but it is. We use it all the time, and it's a great way of showing some order to what is otherwise pretty random elements and things. And basically, we need to know the historical importance of this. Now, it's evolved well back in the 1800s. And they're actually ordered according to atomic mass. Now, nowadays they're not, but they were back then, so you need to know that little point there. And 1817, Dobereiner had a good go at it, and he came up with triads. And Johann Dobereiner grouped the elements according to characteristics. He'd seen some kind of trend here in characteristics. He realised that elements look very similar. So things like chlorine, bromine, iodine, they had a very similar smell. They were different properties in terms of liquids and gases, etc., and solids. But he still nonetheless looked and seen some kind of pattern. He had similar characteristics, and he basically said that bromine had a mass that was halfway between chlorine and iodine, so he wasn't actually too far off with that one. And he noticed this trend and said, right, we're going to group these into triads, into threes. And basically, he gave it a good shot. He tried. Okay. Little bit later on, 1863, Newlands came up with this rule called octaves. Okay, and it was John Newlands, and he grouped elements in order of mass. And he noticed that every eighth element had a similar property. So actually, that's not bad. We're pretty close to what we had before. And he basically likened the pattern to octaves on a piano. And so he called it the law of octaves. So he was quite musical, and he realised that every eighth note. Now, I'm not musical whatsoever, but every eighth note, you had scales, didn't you? I'm sure the musicians amongst you will probably correct me, but he basically came up with this pattern. He said every eighth element had a similar pattern. And basically his theory broke down, though, when some of the transition metals didn't fit his pattern. So he gave it a good shot, but not quite there. But he did improve on what Dobereiner had come up with. So it wasn't until 1869 that Dmitry Mendeleev, came up with the current periodic table that we have today. Okay, and he basically took Newland's work and he adapted it. And he basically still ordered the elements by atomic mass. He still did that. But the big difference is Mendeleev actually left gaps. He was quite smart at actually doing that. Left gaps where elements didn't fit Newland's theory. So this meant that the elements were now grouped in terms of similar chemical properties, a little bit like what happened with Dobereiner. And he actually took the two things and merged them together. And yeah, he was so confident in his theory that he could even predict the properties of undiscovered elements. And this is where he left the gaps. So he's a right smarty pants. So no, he did pretty well, and that was really the power of the periodic table. That spurred scientists on to try and find these elements that Mendeleev had left out because he didn't know they existed. But actually, his predictions turned out to be true. So he was pretty remarkable, really, at the time. Obviously, we have the modern periodic table. Today. However, the difference is that these elements are not ordered by proton. Are not ordered by mass number, they're ordered by proton number. So there is a difference between, obviously, this one and what Mendeleev came up with. And we have groups, these are in columns. The elements in the same group have the same number of electrons in the outer shell. So group 1s have 1 electron in the outer shell, for example. So the group number relates to the number of electrons, like I say. So group 2s have 2 electrons in the outer shell. The elements in the same group have similar properties. So, for example, group 1 elements react with water with increase in vigour as we go down the group. So there is this trend here. Periods are in rows, so these go across, as you can see, going across here. And elements in the same period have the same number of electron shells. Okay, so basically this is period 2, so they all have 2 electron shells. These are also known as S block elements, the ones in red. These are known as P block elements. These are known as D block elements. And these ones are known as F block elements. So as long as we can kind of categorize these into blocks, obviously according to the orbitals that we have, S orbitals, D orbitals, so these elements here, they have their highest energy electron in the P orbital. That's what we call them P block elements. Okay, so we need to know about ionization, because this is periodicity, so we're going to look at trends going across periods and groups, some group stuff as well. So ionization, we're going to look at the trend in ionization. So ionization energy is the minimum amount of energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. So make sure you can recall that. Here's the equation for it though. Sodium gas producing sodium ion, which is also in the gaseous state, plus an electron. First ionization energy for this one is plus 495.8 kilojoules per mole. Always include your state symbols. Never forget them. Remember, this definition says 1 mole of atoms in the gaseous state. Okay. Ionization requires energy. You need to put energy in to do that. So all ionization is endothermic, so it has a positive value. Shielding, right, you'll see this a lot in this video. Shielding, you'll be sick of hearing it, I imagine. So the more electron shells we've got between the positive nucleus and the outer electron, the easier it is effectively to remove it. There's a weaker attraction. This is because we've got more shielding. So shielding is just the effect of the electron shells between the positive nucleus and the outer electron. So you'll see that quite a bit. The atomic size, basically the bigger the atom, the further away the electrons are from the nucleus, and basically the attractive force between the nucleus, positive nucleus, and the outer electron is reduced. So that means the bigger ions or atoms, it's easier to remove electrons from these if they're bigger. And the final one is nuclear charge. So basically this is the amount of protons in the nucleus. The bigger this nuclear charge is, the bigger the attraction is between the nucleus and the outer electron, and the more energy required to remove that electron from there. So this is very important. We're going across periods because we have very similar shielding, but we have more protons as we go across the period. So that's going to have a big effect on how easy it is to remove that electron from the shell. Okay, so let's have a look at these trends, and we're going to look at it in terms of groups first. So ionization energy decreases as we go down a group. So here we've got group 2 elements. We're starting from beryllium going to barium. So the atomic radius increases as we go down the group, so it gets a bigger atom. Outer electrons further from the nucleus, and this means the attractive force is weaker. The energy required to remove an electron decreases. We need less energy to remove an electron because the atom gets bigger. Shielding increases quite a bit, obviously, because the atom gets bigger, we're getting more electron shells between the nucleus and the outer electron. So because we've got more electron shells, the force is weaker, and the energy required to remove that electron reduces. So we've got 2 reasons here: atomic radius increasing, shielding increasing. And basically this provides strong evidence for shells in atoms and proves Niels Bohr's model of the atom is correct. Remember about the history of the periodic table in module 1. So this proves it is correct, but it didn't explain data shown going across periods, which we'll have a look. So this is going down a group. Okay, so let's look at first ionization going across a period. So basically the ionization increases overall as we go across a period, so it becomes more difficult to remove an electron. There are some exceptions though, which we'll look at. So yes, we have this general increase. This is because we have more protons in the nucleus as we go across the period. So this means we've got a higher nuclear attraction. Shielding is similar. Always talk about shielding. Very similar. And the distance from the nucleus actually marginally decreases. It becomes a little bit more difficult to remove that electron, but the shielding is pretty much the same or similar. More energy is required to remove that outer electron, and the ionization energy increases generally as we go across a period. So that's the general trend. But you see, we've got these 2 exceptions, particularly here at aluminium and sulfur. We're going to have a look at them as well. Okay, I should say the period 2, it's the same trend. Obviously, these are for period 3. Period 2 is the same. Okay, so let's have a look at this decrease in aluminium. This is evidence for atoms having subshells. Okay, so the outermost electron in aluminium sits in a higher energy subshell slightly further from the nucleus than the outer electron in magnesium. Okay, so let's have a look here. Magnesium, you can see the outer electron sits in the 3s2. Aluminium, though, has got this electron in a suborbital. It's a little bit further away from the nucleus, and it's slightly shielded from the 3s as well. So you can see here, there it is, it's in the 3p subshell. Magnesium has its outer electron in the 3s, but the atomic model Niels Bohr came up with didn't explain these subshells, so there was a bit of a problem here. Okay, so basically this is evidence that Bohr's model wasn't quite correct. Remember, Bohr came up with the shell theory. The trend is the same for period 2 as well, so make sure you know why that decreases. This is because of this subshell, the subshell stuff here. Okay, let's look at sulfur. Sulfur is a little bit more complicated, so it drops here. Basically, we've got a decrease at sulfur is evidence for electron repulsion, okay, in an orbital. So that electron repulsion, make sure you remember that bit, okay. So phosphorus and sulfur both have outer electrons in the 3p orbital, okay, which is fine. There it is, look. There's this is the energy diagram for sulfur. You can see it's got the outer electrons in the 3p, but phosphorus is only one behind, so basically we just take one of these electrons away, and we've still got all the electrons in the 3p. So the shielding is the same. You have no difference in shielding. However, removing an electron from sulfur involves taking it from an orbital with 2 electrons already in. So we get a bit of repulsion there. Okay, so there it is. The electrons repel each other. Less energy is needed to remove an electron from an orbital with 2 electrons already in it. Okay, this is the one for phosphorus. Phosphorus is already singly occupied, so that's fine. But sulfur has an electron that's paired up with another electron. These repel. It's not going to put up much resistance. When you remove this electron, it drops marginally at sulfur, and then it starts to increase again from chlorine and argon because of the increasing number of protons. Okay, make sure you can explain that. It's all about electron repulsion for sulfur. Okay, similar trend for period 2 as well. I think you get the idea. Right, successive ionizations. This is where we take an element and we just keep taking electrons from this element. We literally strip it of electrons. So when we remove more than one electron at the same time, we call it successive, like I say. So here's an example. Magnesium. Magnesium has obviously already lost an electron here because this is magnesium ion, Mg+. Remove another electron and we form Mg2+. This is called the second ionization energy. It has a value of plus 1450 kilojoules per mole. Again, endothermic because we require energy to remove it. Now you can see we've got these jumps in this graph here. This is the removal of electrons from magnesium. Okay, we've got jumps here. This is because we're taking electrons much closer to the nucleus. We've got jumps in energy. So we need most energy to remove these two. So these 2 electrons are going to be the ones closest to the nucleus. And these 2 here are going to be the ones that are going to be furthest away from the nucleus because they require less energy. But you can see we've got these jumps here. We'll have to explain these jumps. So we've got general increase in energy as we're removing an electron from an increasingly more positive ion. So we have this general increase. Make sure you can explain that. So let's start here. These are the ones that are further away from the nucleus. So these are the ones in the 3s orbital. The next lump are the ones in the 2p orbital, the second shell. Now these ones are much closer to the nucleus, and they will remove them from something that's increasingly becoming more positive, so it requires a lot more energy as we go across. And the last 2 are the electrons that sit in the 1s orbital. These are the ones much closer to the nucleus. So we know this is magnesium as we're removing 12 electrons in total, so we can identify this graph as magnesium because we're removing 12 electrons. Okay, giant covalent structures. So in the previous videos we've looked at giant ionic. This time it's giant covalent. So we need to know some examples of these, and graphite and diamond are examples of these. So let's have a look at graphite first. Graphite is basically made of carbon. Each carbon's bonded 3 times, and the 4th electron's delocalized. You can see these dotted lines represent them delocalized electrons. So we've got lots of strong covalent bonds, means the graphite has a really high melting point. So we've got lots of bonds between the carbons. It's made of layers. They slide over each other really easily. We have weak forces between these layers. And this is because we have these delocalized electrons. And also, these delocalized electrons give it another property, which means it can conduct electricity. Unusual for a non-metal. And they carry a charge. That's how they can conduct electricity. And the layers are really far apart in comparison to the covalent bonds. This means graphite's got low density. It's quite light, so ideal for things like pencils. Graphite's insoluble, it doesn't dissolve in water. This is because the covalent bonds are far too strong to break. So thankfully you can put a pencil in water and it won't dissolve. Okay, diamond is a little bit more precious. The same type of setup in terms of we've got carbons bonded to each other. However, each carbon's bonded 4 times in a tetrahedral shape, so the structure is different. Really tightly packed, rigid arrangement, conducts heat well, and obviously this is a really high strength material that's really hard material, and it's formed from volcanic eruptions. Unlike graphite, diamond can be cut into gemstones, so obviously because you can use it in jewelry. Very high melting point, lots of strong covalent bonds, really, really hard, really difficult to melt. I mean, like really difficult, it's really, really high. Diamond doesn't conduct electricity, doesn't have any delocalized electrons unlike graphite, and also, like graphite, it is insoluble. Same reason, loads of covalent bonds, really strong, difficult to break. Silicon also has the same structure. You'll probably see silicon as well. Same reasons. Silicon forms this giant tetrahedral structure, and so make sure you can apply the same rules to silicon too. Okay, another one is graphene. Now this is quite new in terms of its use anyway. Graphene is one layer of graphite, so we know we looked at them layers. It's one atom thick, made of hexagonal carbon rings. You can see a diagram here. As graphene is only one cell thick, it's lightweight and it's transparent, crucially. And what we have is we have delocalized free-moving electrons amongst this sheet here. Excellent conductors of electricity because they can carry a charge, like I say. Same delocalized electrons, they strengthen these covalent bonds as well. Gives graphite this really high strength property, so we can use it for things which are electronic devices that we need to maybe use if they're mobile, because it's lightweight and also it's transparent, so we can see through it. So it's got some pretty useful properties. And the uses are aircraft shells, so that's pretty useful. Supercomputers and high-speed computing, so things what they might have at the Met Office. So they'll have these types of, processors that you made from graphene instead of silicon, and smartphone screens. So they're used from that. Again, you like touch screens, you touch it and it converts some of the energy that's been put in for touch into electrical signal, and obviously it processes the information that you've told it to do. So there you go. Metallic bonding. Right, so metals have giant metallic lattice structures. Okay, this is relatively straightforward, shouldn't pose too many problems. Positive metal ions formed in the middle. They donate these electrons from the ions, and they form this sea of delocalized electrons, a little bit like in graphite. They have electrostatic attractions between the positive metal ions and the negative delocalized electrons, so that's quite important. That's what holds these things together. The more electrons an atom can donate to the delocalized system, the higher the melting point. So obviously that's quite important. And obviously magnesium has a higher melting point than sodium, because magnesium can donate 2 electrons. Remember, sodium's in group 2. Sodium only donates 1 per atom, because that's all it can do. Metals are good thermal conductors. They have delocalized electrons. These electrons here, they can move, so they can transfer their kinetic energy when they're heated up. They're also good electrical conductors, no surprise there then. Again, delocalized electrons, they can carry that charge, or they can carry the current running through the metal, so metals are good conductors. They have high melting points as well, lots of strong electrostatic attractions, holding these delocalized electrons and positive ions together. And solid metals are insoluble, they don't dissolve in water. The metallic bond is far too strong for it to break, and that's why they don't dissolve well in water. Okay, so let's have a look at some melting points, and we're going to look at melting points of period 3 elements. So the first 3, sodium, magnesium, aluminium, they're in. These are obviously all in period 3. These all have metallic bonding. Okay, so there it is for sodium. You can see it's got 1 electron per ion, delocalizes. Whereas for magnesium, you can see we've got 2 electrons. We've got a double charge in the middle, and so therefore that's the metallic structure for magnesium. Basically, we've got this general increase in melting point as the metal ions have an increasing positive charge, so bigger charge, more delocalized electrons, and a smaller ionic radius. So magnesium has a smaller ionic radius than sodium. This means that we have a much stronger, higher charge density, a much stronger attraction between the negative delocalized electrons and the positive metal ion. So this is the metallic bond. Okay, we need to know this same trend as well for period 2, and luckily it's just the same. Okay, so let's have a look at silicon. So silicon's right at the top there, it's like a mountain. So it's in period 3, it has a giant covalent macromolecular structure. It's a non-metal. Obviously we looked at silicon just earlier. So silicon has the same structure as diamond, except obviously it's got silicon atoms in there. Lots of strong covalent bonds. These hold these things together. Loads of energy is needed to overcome these strong bonds between these silicon atoms. So therefore, it has a really high melting point. In fact, really high compared to everything else. Okay, and this is the same for period 2 elements. So, for example, carbon as well. Okay, let's look at phosphorus. Now, phosphorus is the formula P4, much lower compared to silicon. Huge drop here. It is just simple molecular structure. It's not giant covalent anymore. The melting point is now determined by weaker induced dipole-dipole forces. Okay, so they are quite a bit weaker in this case. So we're not talking about breaking covalent bonds. We're talking about weak intermolecular forces. So an induced dipole-dipole. Phosphorus is P4. Make sure you remember that as well. Sulfur, it goes up a little bit here because it's going all over the place here. Sulfur has a formula S8. Still simple molecular, just like phosphorus. However, because it's got 8 sulfur atoms in it, it's a little bit bigger. It's got a bigger mass. Therefore, because it's got a bigger mass, a bigger molecule, we have stronger induced dipole-dipole forces compared to phosphorus. And that's why it rises a little bit for sulfur. Okay, same trend for period 2. I think you might be getting the idea here, so they could ask you on either of them. Okay, let's look at the last two. Chlorine has the formula CCl2, much lower than any of the others. It's a really small molecule. It's a simple molecule, just like the rest of them. Small induced dipole-dipole forces, lower melting point. And argon at the end there is even smaller. It doesn't even bond with anything. It's just on its own. It's just an atom, monoatomic. Again, same reason, less smaller atom there compared to the molecules that we had before. Smaller induced dipole-dipoles, and therefore it's got a lower melting point. Lowest of all of them, actually. Okay, it's the same trend for period 2. I think you probably get the idea there. Okay, so let's just summarize all of the different type of bonds that we need to know then here. So some of these you might have seen summarized already. So your giant covalents we've seen in this video here is silicon dioxide. They're generally solid. They don't conduct electricity when they're solid or liquid. So graphite's the only one that conducts, and graphene as well, formed from graphite. They don't really melt anyway. Really difficult. They're normally sublime. Soluble in water. No, they don't dissolve because they've got really strong, loads of bonds. High melting points because you've got lots of strong covalent bonds. Simple molecular, similar to simple covalent. They're basically a covalent bond, but these are just little molecules: iodine, ammonia, water, liquid or gas at room temperature. They don't conduct solid, don't conduct when they're a liquid. Electricity. Soluble in water, depends on the polarity. If the molecule's polar, it will dissolve in water. If it isn't, it won't. Melt point low because we're only breaking weak forces. We're not breaking bonds, remember. Giant ionic, metals and non-metals bonded together, a bit like this. Normally solids at room temperature. They don't conduct when they're solid, but they will when they're a liquid because the free ions are free to move around. They will dissolve in water because they've charged, and so water's polar, so that will break it down. High melting boiling points because you've got lots of strong electrostatic forces that you have to try and overcome. The final one is metallic. These are just metals: magnesium, sodium, copper, whatever that is. Any of these different types of metals. So usual state at room temperature, solid. Does conduct electricity when it's solid because it has delocalized electrons. This time it's two things: either ions or electrons will allow a charge to be carried. They will do it when they're a liquid as well for the same reason. They're not soluble in water, don't dissolve very well in water, and melting point is high. Again, lots of strong electrostatic forces, just like giant ionic. Yeah, so this polarity bit's quite important as well. So polar molecules, they will dissolve well in polar solvents, but your non-polar molecules, hydrocarbons, don't. If they're non-polar, they won't dissolve in a polar solvent. Okay, and that's it. That's a pretty much a summary of the periodicity topic. This is for OCR A. Please subscribe to this channel. If you just click on the little button in the middle of the circle with my face on it, so if you click on that circle there, you'll be able to subscribe. Much appreciate your support in this. Also, if you want a copy of this PowerPoint, if you like what you see and you want a copy for yourself, please click on the link in the description box and you can purchase it from there. But that's it now. Bye bye.